Hi everyone, my name is Emil Tsalaparis and I'm with the RCS lab at the University of Waterloo, working under Professor Ali Masizadeh. Today I'll be presenting Aurora, an OS level service that provides persistence to applications. The motivation of our work is that persistence is hard. It is very easy to lose data because of a bug in the application code that checkpoints and restores state, or even in the interactions between the application itself and the OS or the file system and because of the guarantees that they provide. Even very widely used programs have had data loss bugs. For example, Postgres has had data loss bugs as recently as 2018 because of interactions with the Linux fsync call. LevelDB, which is used by Chrome and Ethereum, has had also multiple data loss bugs throughout the years. So we see that this is far from a solved problem. So what we want to do is provide a tool for developers to easily create persistent applications. We do so by unifying all non-volatile and volatile storage under one unified model so that the application developer does not need to worry about what data is where. We do so by creating persistent processes rather than data. It is not enough to just put all our data in NVDIMS to provide persistence at that level, because there is always information in the CPU or in the system in the form of registers or open Unix resources that cannot be saved in that way. So our idea is based on single-level stores, and single-level stores have existed for a long time, since 1962, and they have been implemented in at various times in the industry, in the form, for example, of IBM's AS400, or in academia, in the form of the Aero single-level store. However, they were implemented at a time when the performance between memory and disk was wide, the performance gap was very wide, and that meant that it was very hard to continuously send data to persistent storage in such a way that it was performant. Nowadays, with the advent of new devices and which have much higher throughput, it is much easier to achieve high performance with a single-level store. So this brings us to our system, Aurora. Aurora is the first POSIX single-level store. It is POSIX in that it supports all POSIX primitives, and it can support all existing POSIX applications. Our design goals were low overhead, so that it can be used continuously with the application, and transparency to the application, so that no developer effort is needed. It can also be used as a base for other mechanisms that manipulate execution state, such as, for example, migration, fault tolerance, and debugging. The Aurora can be used either through the command line without modifying the application at all, or through the application itself for higher performance by using our own custom API. The main part is the kernel modules, which is in the kernel and is comprised by a continuous checkpointing module, which creates these execution images, the object store, which stores this information in persistent storage, and the file system for backwards compatibility with existing applications which use file semantics. Single-level stores do not have files. The challenges in our work were making checkpointing fast, and therefore we needed to identify performance bottlenecks. We needed to gather process state and modify page tables very quickly because this was done with the process stopped. And we got gains by minimizing changes to the page tables. We also minimize page faults. The copy and write mechanism that we use causes a lot of minor page faults as the process copies stuff lazily. By optimizing in such a way that we do not destroy all mappings, we get higher performance than, for example, fork-based mechanisms. We also dump to disk efficiently and dump in such a way that both checkpoints and restores are quick. This is important because while dumping to disk is done concurrently with application execution, it's not quick. It bounces checkpointing frequency. In conclusion, Aurora is still a work in progress. It has been implemented in FreeBSD 12 and is comprised of about 1,400 lines of code. We are working on further optimizing performance using NVDIMS for tiered storage and having improved network supports for sending checkpoints across the network. I think my time is almost up, so I'll be happy to take any questions.
Great, next speaker. And next speaker, go ahead and get set up while he can answer a question. How do you say your name? If there are no questions, let's thank our
I have one question.
Oh, I'm so sorry.
Just took me a while to get here. So a lot of programs have this bad habit of getting kind of corrupted, and the only way to really get them going again is to restart them. So how do you deal with the program that's just kind of belly up?
So unfortunately, bugs in the program corrupt state in such a way that we cannot really do anything. We could rewind the program to a point before it was corrupted, but we would need to actually find out when the bug happened. So this is not really possible. So we only cover events such as, for example, power failures that are external to the system, or maybe OS level events that cannot happen again if we restore.
But you do have the ability to roll back sometime?
Absolutely. We can roll back at any granularity depending on what the user wants, and if there is enough data, we can have we can rewind at arbitrary time lengths.
All right, great. Thank you.
Thank you very much.
Thanks, Anu.
Thank you.
So you can go ahead and advance the slides. So our next speaker is Patrice Luca, and he'll be talking about Phobos.
Thank you. Good afternoon, everyone. My name is Patrice Luca. Let me introduce Phobos, a scale-out object store implementing tape library support. I work at CA, a French research agency, which designs and operates a very large HPC simulation cluster that produce a large amount of data. I'm part of a team which is in charge of designing storage system able to ingest petabyte of data per day and to store exabyte for a long time as safely as possible and with low cost if we can. To address this challenge, Object Store seems to be a promising solution due to very simple put, get, delete API on immutable object. They deliver easily very good horizontal scalability. But often they are mainly designed for using disk, hard drive, flash, SSD, and VME. Whereas magnetic tapes, magnetic drives, tape library remains a good solution, a safe long-term storage at low cost. That's why we have been developing for a few years Phobos, which is a parallel heterogeneous object store. Phobos manage distributed set of file system to store objects in this file system on different storage media technologies, from hard drives, for example, to magnetic tapes. Phobos aims to optimize I/O access depending on the storage technology. For example, if you use tape, Phobos takes care of minimizing data sinks for magnetic tapes. Phobos is open source, built on top of existing widely adopted standards to avoid any private technology locking. For example, we use LTFS, linear tape file system, as file system to format tape and to store object on tape. Phobos is able to directly manage tape library using SCSI driver. It supports all common tape drive model. Let's focus on the current big picture of the architecture of Phobos. We use an I/O adapters to fit multiple storage technologies, POSIX and LTFS, for example. We can plug on different layouts to implement different performance and fault tolerance level. Currently, we have, for example, a mirroring layout to store object with using many different replica. Phobos is able to attach any tag to any media. It's a very simple and convenient way of implementing storage partitioning, for example. Phobos architecture is a distributed one with many different distributed components. One very important component is the resource scheduler. The resource scheduler optimizes, for example, tape fill rate and minimize tape mounts. We choose to store metadata using a k-value only schema. It allows us to store metadata on scalable distributed NoSQL database. We also saved within object this metadata on media for recovery or tape import purpose, for example. That's a still continuous in progress development. So as perspective, we plan to add new connectors. In addition of our current command line client and API, we plan to add S3, Swift, and NFS connectors. New layout, in addition of mirroring, as striping or erasure coding. New adapter like NVMe or over object background like S3 or over recursive Phobos system, for example. Media lifecycle management is a very important topic for us. We want to optimize migration between storage technology. And we optimize resource scheduling policy, prioritizing, and grouping I/O. Let me finish by 2 use cases. We use Phobos in production since 2016 at CEA to store multi-petabyte genomic data set produced by DNA sequencer. We receive this data on our computing complex. We store first in Phobos before migrating this data to our HPC data cluster. And an upcoming use case, we plan to use Phobos as a Lustre HSM backend. We massively use Lustre as a POSIX user frontend in our system. And we plan to use Phobos as a high-performance scalable archive backend. OK, that's it. Phobos is open source, so please feel free to download it and use it and give us some feedback. Thanks for your attention. If you have questions.
Perfect. Thank you. All right, 45 seconds for questions while the next person gets set up. Any questions? And I'm looking this way this time when I ask. Any questions? All right, next up is Duo Zhang from Iowa State. I'll just let you started. Go ahead.
Okay. Hello? Okay. So, okay. Hello, everyone. My name is Duo Zhang from Iowa State University. I'm a PhD student. So today, I'm going to present a cross-layer approach for diagnosing server system failures. This is a joint work with Western Digital. So server system failures are damaging. They may result in data loss, server downtime, and so on. Unfortunately, it's very hard to diagnose these issues. There are typical steps to fix the issue. First, users may observe some failure symptom. Second, users may report this problem to the developer. Then the developer will reproduce these failures. And after that, we have a bug triggering workload. The bug triggering workload is not as same as original one. This bug triggering workload is very small. So after that, the developer try to pinpoint the root cause. And if we are lucky, we can get a patch to fix the bug, fix the issue. So our work is focused on the first step, how to pinpoint the root cause quickly. So this step is very time-consuming and needs lots of human efforts. So for example, let's see the Algolia case. The Algolia data center server crashed, and the developers try to pinpoint the root cause, spend lots of time, but get a wrong conclusion. Samsung SSDs were blamed and blacklisted. Until 1 month later, a Linux kernel bug was identified as root cause. So there are many existing tools, such as S-Trace and Bug Analyzer, for diagnosis. But all the tools are focus on single layer. So this is not enough. Our approach XDB is different. We leverage virtual machine to capture cross-layer information to generate a dependency graph. And we apply the rules to identify suspicious events. So our platform has several advantages. First, it can support a modified software stack. Second, it doesn't require special hardware. The last is it can identify anomaly automatically. So the idea is simple, looks like, but there are some key challenges, such as how to synchronize events precisely across layers, how to treat fine-grained functions, how to define rules, and how to minimize disturbance and overhead. So we have some solutions and built a prototype on QEMU, also ran some cases on that. So let's see a case in detail. Researchers found many serialization errors under power fault on Linux kernel on different SSDs. And we applied our XDB to get a dependency graph. This graph is so big, but we can narrow down that based on some rules. Because the device state can change the service system failure depends on the device state. So we can apply this rule to this one. So we can get some suspicious passes. Let's zoom in the path. Right here, we apply another rule. The fsync system call involve block dive fsync, the kernel function, and finally generate sync catch command. But we didn't find the sync catch command on the suspicious path. So this is the result we think. So as I mentioned earlier, so the previous work was performed on a lower kernel 2.6.32, and the failure may or may not happen on different kernels. So we repeat the experiment on new kernel, and we found the symptom is different. So let's compare the result and see the difference. We see the block dive sync generates a sync cache command on the reference graph, but it doesn't on the original graph. So that means the block dive sync function is problematic. So note that if the rules are specified, we can check the rules automatically based on the graph. So that is the end of my presentation. Thank you. I'm happy to answer questions now.
Thank you. All right. Questions? Next speaker. Get set up. I think we're good this time. Okay. C, I'm going to give you I'm going to give you a warning. I'm going to give you 3, 2, 1. Okay. Just scroll down. It's in the same PDF. I'll give that to her. Oh, she has. Okay. Then give that back. Okay. Great. And then go to View, and then play slideshow. You got it? Yeah, actually. Yeah. Can you help her start the slideshow? Just go to View and play slideshow. Just get right at the bottom. Scroll down. All right. Our next speaker is C. Chen talking about census. Go ahead. I don't think your mic's working.
It just started.
Go. Start. I think it's working now. No. I mean, I could just give them this. I could give them the handheld. Yeah. Let's just do that.
Hello, I'm C. Today, I would like to tell you about sensors counting the interleaved workloads on shared storage. So shared storage quite common nowadays. If we want to give fair resource provisioning, we'd better have a better understanding of the functional distinguished usage of the storage system. So there are several challenges. One is multi-tenants, and also the workloads are dynamic and interleaved. And most importantly, our method should not have high computational cost. However, existing approaches fail to distinguish the interleaved workloads, especially when we do not know the number of concurrent workloads. So we suggested the sensors. It's a classification framework that combines the time series analysis and gradient boosting to identify the number of concurrent workloads. So the time series analysis let us be able to extract thousands of features. These features are totally different from the traditional ones. It's much expanded features what we have. And we use gradient boosting because we want our model to be interpretable. Much more, it's more meaningful than the black box of deep learning. So this is our architecture of sensors. So we are interested in the logical block address and delta of time of each access. So we have a sliding window of 10 minutes and to segment the whole block I/O trace. So for each segment, we use TS-Flash, the time series analysis tool, to extract many features, and then we select the features and put these features into the classification model, and then to predict the number of concurrent workloads. So on the left figure, you can see a list of different features. We listed according to the importance of features. So we tried these models on 3 different data sets. The first 2 are public available traces, and the last one is we newly attracted from our server. It's 30 days of block I/O trace that we run the machine learning training workloads on it. So our version is that although the order of the top important features may differ from each data set, generally speaking, all of the top features come from the consistent categories. So we dig into these features and give them the system readable explanations. So here I give an example of the features. It calls address complexity. On the left is a math explanation of these features. So we discovered that there are high correlation with the feature and the number of concurrent workloads. So we use 2 kind of metrics to evaluate our model. One is X accuracy, it means approximate accuracy, and also the map is the mean absolute percentage error. So our baseline, we call it the fairness guess, is a randomly generated label based on the distribution of our training set. So the result is optimistic. So the sensors generally can have quite high accuracy, much better than the baseline. However, we also can see that on certain cases, it does not perform well. So we discovered that this may be because of the distribution of the, and our training set does not have even distribution. So we believe that if we have more data sets, maybe our model will have higher accuracy. To sum up, the sensors could capture the fundamental patterns from I/O trace with quite high accuracy. And also sensors expand the feature explanation field so we can benefit for our storage community. And also we find that in our case, the time-related features is not that important as we expected. So only 30% of the top features are related to time, so only affecting the 1% of the final result. Okay, thank you.
Yeah.
Okay, yeah.
So the question is, why do you need to identify the number of workloads, especially in the case that the workloads do not identify themselves, like for spatial processing with priority, while the storage system by itself need to identify them or distinguish them?
You mean why do we need to identify the?
Yeah, why we need to do this, right?
Because if we know the different workloads, we can separate them. And then we may, if the system is not busy, then we could group these workloads, these assets together. Then when we fetch this address, it will be more efficient.
Hey, Nick Cumulo. How much of a window is needed to start classifying a new workload? Like, say some new client joins and starts talking to the storage. How much time would it take to know if this client is part of an existing workload or a new one, or what it's doing?
So now our method is the offline model. So because our features is quite big, so the training time is may take 300 seconds. So it's a bit long. But later, if we can further improve the compact features, maybe the time will be shorter. So we also think of make this to be online.
Cool, thanks.
Hello everyone, my name is Ji Zhang. I'm from the Huazhong University of Science and Technology in China. And I'm currently a PhD student, visiting PhD student at New York University. Happy to be here to introduce our latest research work on adaptive and tail disk scrubbing scheme. And there are two typical applications on machine learning for improving the reliability of the storage system: disk failure prediction and sector error prediction. And some researchers on the complete disk failure prediction still suffer from a 1% false positive rate, which makes it difficult to put them into production in real-world centers. And although the false positive rate of the sector error predicted results tends to be larger than the complete disk failure, these methods do not force the operator to replace the disk, instead only apply simple operations like disk scrubbing. And existing studies for disk scrubbing based on the sector error predictions have several limitations. First, this method takes a single snapshot of smart attributes as training data for prediction without considering the sequential dependency between the data for prediction and the second is the method not only apply binary classification to the status of the sector and cannot quantify the distance to the actual sector error happens. Therefore, they only accelerate the scrubbing at a fixed rate and result in unnecessary scrubbing cost. And third, these studies simply increase the scrubbing rate for the full disk without considering the areas that have a higher probability for encountering sector errors. And thus, they also do not explore how to scrub these higher risk errors in advance based on I/O operators. And solve the limitation 1 and 2 at the disk level, we propose an adaptive scrubbing rate controller So for the limitation 3, we explore the locality of the sector errors to locate the high-risk errors at the sector level. And so for the last limitation, we propose a piggyback scrubbing strategy at the I/O operations to further improve the efficiency of scrubbing. And we proposed an adaptive scrubbing rate controller that contains an LSTM-based model to not only predict whether a disk has a sector error, but also predict the sector risk degree for all the disks in the data center. And we leverage our predict result to determine an adaptive disk scrubbing rate at the disk level. We also explore the locality of the sector errors, which means there is a higher probability that it happens in the vicinity of an existing error. Based on these findings, we focused on these higher disk errors. In construct to the sequential scrubbing, once the application I/O operations access the higher risk errors, our proposed piggyback scrubbing strategies immediately scrub the fragmented sectors untouched by the I/O operations. And it will reduce the scrubbing cost because we reduce the frequency of head movement for the fragmented sectors. And we use the error under the receiver operating characteristic curve to evaluate the binary classification performance, and also use the classification accuracy to evaluate the multiple class classification performance. Our predictors achieve good predict performance in all cases compared to the state-of-the-art method. And we use the 3 real-world workloads from the Tencent company and found our scheme can decrease 80% of mean time to detection while decrease 20% of the scrubbing cost compared to the state-of-the-art scheme. So if you are interested in our work or have any questions, feel free to contact us. Thank you.
Okay. It's on, right? Okay. Yeah, I'm ready. Okay, so let's. How come the return doesn't seem to work? Down here. No? Okay. No. Okay. This one? Okay. On the desktop.
Like a video game. Okay. This is cool. So I got tasks. I can click on that. I did that. I'm opening it. Okay, cool. Oh, right. What's the name of your tab? Flash?
Sanjeev. Sanjeev.
Let's see. Sanjeev.
Yeah, Sanjeev.
Sanjeev Fast Whip.
Right.
Okay. Does that look right? Okay, cool. Opening. Blah 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 blah. Optimal configuration of cloud storage gateway. How about that?
Okay, thank you.
Super.
All right, my name is Krishna Kant from Temple University, and this work is from my two students, Anish, who has already graduated, and Sanjeev, who is presenting another talk at a different conference. So I'm the one presenting the talk here. Okay, so this is about the configuration management, and in particular, the configuration management of cloud storage gateway. So let me start with telling you what cloud storage gateway is. How is that? How come the arrow doesn't work? Yeah, it doesn't work. Okay. So, so let's see here. But I hope I don't have to do this for every slide. Okay, this one is working now. All right, sorry. Okay, so the cloud storage gateway is essentially a mechanism by which you put some local storage on your local site, and you access it using a block storage API. But on the back end, it's backed up by object storage, which is available in the cloud. And really, the idea is to try to satisfy the requirements of different workloads, even though you have uncertain latency on the back end going to the cloud. So configuring this kind of a system is quite challenging, and because there are a lot of parameters in terms of how much local space you're going to give to the data and the metadata, and also in terms of how much compute power you're going to deploy, how much memory bandwidth, and so on and so forth. Okay. So those are the sort of the challenges, and it turns out that if you don't configure this right, then there could be SLA violations and application timeouts. And also, it turns out that if you just blindly throw resources at the problem, then it doesn't seem to work very well. Okay, so we looked at this problem, and we first of all collected a lot of data. We did an experiment on a real cloud storage gateway. We had 1,000 data points, ran a bunch of workloads that you can see are listed, going from tiny to the large. And based upon that, we want to come up with a way of configuring this. So what we found is that it's difficult to model the performance. We use machine learning for that instead, and you find out that going forward, that is from the configuration to the performance, works pretty well, and you can get 90% accuracy or better, but other way doesn't work very well. And therefore, to go the other way, we basically did a technique where we use this forward model as an oracle, along with a optimization technique, which in this case is genetic algorithm, but we want to do this very intelligently, taking into account the importance of different features and the relationships between the different features. So here is the importance of the various features. You can see, for example, the local cache is the most important, and so on. And then by using this intelligent GA, we can get a significantly faster convergence, as you can see here, and we can get a much smoother operation of the GA than otherwise. Now, there's a lot of additional work to be done here in terms of applying this methodology to a number of different applications, and also trying to use monotonicity and the modularity and unimodularity and other properties to make this even faster. And I'm done.
Perfect. You didn't need extra time at all.
Yeah, I didn't want to go through the entire process of like not understanding how to use a Mac, so I did this. So yeah, I'm going to present my work in progress on fuzzy cache, which is a caching mechanism for emerging storage hierarchies. Before I start off, I just want to talk about the premise on which our entire work is based on. It's a very simple basis, that is, with the advent of storage technologies which are much faster now, such as Optane, does it actually make sense to use traditional caching mechanisms that spend more resources on prefetching and actually spends more resources on cache itself? So we argue that it's better to revert to a simpler mechanism that has less overhead. And also, maybe we also argue that it does not make sense to cache everything that is requested for. So we bring in a mechanism which is fuzzy cache, which only caches popular cache candidates. We've used frequency as an attribute to determine whether that cache candidate is popular or not. Yes, there are other attributes which we can consider later on, but for this work, for now, we've considered frequency. So our architecture in fuzzy cache consists of two caches, one of which is a simple LRU data cache. So it's a low overhead cache. It's a block cache where both of these caches treat the underlying storage, the Optane, as a block device. And we have a dynamic metadata cache, which is nothing but LBA and frequency table. So it stores the LBA, not the data, for the corresponding block, and it also stores the frequency of access. So what happens in the dynamic metadata cache is that after every window of accesses, there is a checking of whether, there's an evaluation of source where you check whether a certain LBA has turned popular or not. And how it is done? It's done by checking whether the frequency of that block has crossed a certain threshold. So this is done after every window of accesses, and there is another operation that goes on in the DMC. What happens is there are certain workloads for which, yes, you do not see accesses that exhibit high frequency for certain blocks. So in that case, what fuzzy cache does is that it reverts to an LRU, which would be a low cost and low overhead solution, where it may not perform the best, but it is the best solution for that workload in question. We've tested it out on 3 different setups to see if our premise is right. That is, we tested it out with DRAM with Optane as the backend and Optane SSD. We tried it with a low latency SSD and a high latency SSD. We tried it on 5 different workloads, 4 of which were from the Spec SFS 2014, and 1 of which was the SNIA web search. We tried different combinations of reads and writes so as to see whether it makes sense for both those operations. For the Optane SSD, yes, it does make sense. The y-axis over here is the average access latencies in microseconds. It does make sense. We can also see that in some cases, LRU actually performs better than the other 2 mechanisms in question, which is ARC and SARC. But fuzzy cache actually performs better in both the cases for the read latency and the write latency. However, if we move on to the low latency SSD as the backend and the high latency SSD, we see that for the low latency SSD, it performs comparable to the other mechanisms, at times worse, but not better. But for the high latency SSD, it does deteriorate. The performance does deteriorate. And that actually consolidates our hypothesis that, yes, it makes sense to rethink traditional caching mechanisms when the technology at the back end is getting faster. And for future work, we intend to look at the tail latency and address the endurance impact. And there are some internal parameters, such as the number of accesses for each window, and also the frequency threshold pertaining to the workload. We want to auto-tune those parameters. We want to treat Optane as the cache itself and look how that works to the next tier in question. And we also want to make that cache change operation more sophisticated. That is, to reduce the switching overhead to the LRU. That's it, if there's anyone who has questions.
All right, thank you. We've got a minute and a half for questions. It's nice work.
Oh, okay. So you make the caching or replacement decision based on the frequency, right?
Yes.
So is this still algorithm that have time complexity of 01?
Sorry, I didn't hear.
Is it still a 01, big 01 algorithm?
Yes, for the lookup. Are you talking about the lookup for?
I mean, you try to find a high frequency or low frequency data to be replaced,
Yes.
you have to select, right, the least frequency to be replaced. Is that still a constant time big
Yes,
O1 algorithm?
That's a constant time operation.
Okay.
Yes.
All right. Turn your night mode off. There you go. All right, which one else is Gary talking about?
I don't know.
Huh? Oh, there it is, corner. There you go.
Hey, so my name is Vishwanath, and I'm going to be presenting on clustering workloads for storage optimization. So we all know that all the companies have like a main memory, but you cannot send all the requests to the main memory since it will crash. So hence, to stop your main memory from getting overloaded, all the main memory is precluded by using caching servers and caching softwares. So one thing is that all of these caching servers cost a lot of money, and to optimize caching means to reduce the cost. Hence, optimizing these storage servers becomes a top priority. Now, to optimize these storage, we need to analyze the kind of workloads that they handle in order to, in order to design these caching systems better. And that is pretty much what my work is and will be, maybe. So the background is that modern day workloads are diverse, but they have some similar characteristics even if they are from multiple sources. So let's say if you have a workload from source A and source B, there is no guarantee that it's going to be statistically different. And there are many works which have proved that these workloads are same, and they have also come up with multiple insights into this data, but not any actionable work has come since then, and that is where I step in, and I have tried clustering these workloads based on different features which I extracted from them. And the existing clustering methods such as RAID are very coarse, and they do not take into fact the metadata or even the features of these workloads for clustering. So to prove my point that many of the workloads are similar, I plotted the read-write ratio and the amount of unique blocks accessed by 105 different workloads. And you can see that there are a lot of these workloads which have very similar access patterns at the same time, and they have very similar amount of blocks which are being accessed. Now, another study that I did was with respect to the interarrival time on the Microsoft Research dataset. Now, in that, so one of the reasons why I took interarrival times is because it tells you how busy a particular workload is and how better you can cluster workloads based on based on how busy they get. So for example, in this graph, you can see that the entire research workload can be fit into the interval between in the requests in your source control 2 or your terminal server. So it does not make sense allocating 3 different servers. You can just have a single one for caching all the 3. Now, similarly, another attribute that I looked into was the block size. So block size is an important feature in any of the workloads, since it gives you an idea of how big a data you're dealing with in each of these workloads. And as you can see, the research workload, which was probably the busiest, was accessing the smallest amount of blocks. So there were multiple quick accesses, but they were all very small. At the same time, the source control 2 had like bigger block accesses, but they were few and far in between. going forward, I plotted the individual hit rate curves of each of these workloads. And hit rate curves give you a good idea about how each workload is performing given a particular cache size. So the x-axis is basically the cache size, and y-axis is the hit rate that you generate by using that particular cache size. So you can see that for all the three workloads, you're not getting 80% and above hit rate. For smaller cache sizes, it only goes to that level when the cache becomes like really large. So I went ahead and performed a naive clustering approach, and it came up with these two clusters for the MSR dataset, which basically gave an 80% hit rate for smaller cache sizes. So this goes on to prove that there is scope in clustering these workloads onto a single caching server to make it more cost efficient by reducing the amount of storage that is being used. So the future work includes coming up with better caching strategies, probably using prefetching, and even analyzing these workloads and coming up with general models to come up with better replacement policies. Thank you.
All right. Thank you, Vishwanath. Questions? All right, next speaker set up.
Hello.
Go ahead.
Hi, everyone. My name is Madhurima. I'm currently working at Intel Corporation at NVMe Solutions Group. And I'm a graduate, I graduated from Temple University. So this work, the flash key, which is a key value store designed for SSDs, is done with collaboration of Temple University and Intel Corporation. And yeah. So, there are a lot of problems with the LSM tree in terms of write amplification, and so it is at application level write amplification. Beneath that, there is some additional write amplification that is incurred due to the FTLs. So, so we try to redesign the key value store particularly meant for the SSDs, and the three challenges that we have looked at is to design a trade-off between the space amplification and the write amplification, that we want to use as much, as low as possible space amplification, yet to have a good write amplification. And then we prioritize, given the performance of the current SSDs, we prioritize more like point accesses over range queries, but still at some point it might be necessary to address the range queries, so we have considered the range queries as well. Finally, we have done the fast recoveries under failure, and there is a trade-off based on the your flushing frequency and your recovery time. So I'm not going to cover that section, but we have taken that into consideration. So this is the design for our key value store, where we have two major structures. There is a flat file-like structure to the right, which is called logical band or L band, where you persist the key and the value in real. And then you have another structure, which is a hash table, that is used for indexing the key value store or the data store. And there is no key or actual value stored in the table itself. And for every entry in the key value store, you can think this white blocks, like in the data store actually, L band. There are a couple of L bands, and we have a hard limit on the number of L bands that you can allocate to, just to trigger garbage collection or compaction at regular interval, because one of our takeaway was, like, if you do frequent garbage collection, that is always, or trigger the garbage collection at regular interval, that is really helpful. And there is a part of LSM tree which is like included on top of the other two structure, but this is a key-only LSM tree. So there is no value stored. This is used just to support the range queries. And this structure is touched only during the insert and the delete operation. No other operation touches this LSM tree. So given that structure, we have tested it against both WiSESV and the DB bench that comes with the RocksDB and LevelDB. And here I'm just recording the performance of DB bench. So these are the workloads that we have tested with 50 million key values pairs. First we have sequentially filled, and then the other workload being run with workload number from 2 to 5. And here we are reporting the latencies under when tested under workload 2 to 5. And you can see for complete read-oriented workload, which is a random read, we achieve better performance in both the cases. So the green bar here is for RocksDB, and the performance improvement or the latency improvement over RocksDB, and the red bar represent the improvement over LevelDB. And we achieve 85% improvement for the random write performance. And majorly for everything, all the workload that we have tested against, we achieve better performance. And this is the metrics for the write amplification. For both LevelDB and the RocksDB, we have seen an write amplification up to 19x for LevelDB and 10x for RocksDB. And we, on an average, saves 4 to 12x for write amplification. And so we do perform as well for better write amplification. And in summary, I would like to say that the first few words that, as I said, like we have this hash lookup. Can I finish this? Okay, so the hash lookups actually saves a lot of time because we do not have to do any tree traversal, and we then use this flat data structure for storing the key value pairs. And we limit the space amplification and keep it very low and trigger garbage collection frequently. Currently, we are working on optimizing some of our structure. That's it. Sorry to
Thank you. That's fine. Questions? You've got about 10 seconds for questions while the next person sets up.
So do you keep the hash table always in memory?
It is designed like a hash table as a file. So you can optionally store it on disk or completely in memory or somewhere in between, but we haven't done any kind of caching.
Okay.
Yeah. So, keep setting up. Next talk's going to be by Soyi Choi from the College of Software. Let's see. Lovely. Take it away, Soyi.
Yeah, hi. I'm Soiche from Sungkyunkwan University in Korea. Today I'm going to talk about our observation results about unexpected write patterns. We have wait a minute. Yes, unexpected write patterns we get from the RocksDB. So before starting let's see about our observation results. We are going to talk about minimal characteristic of the flash memory SSD. Flash memory SSD is really friendly to the small, large sequential write in SSD. Yeah, it is very well known that in flash memory SSD, the small random writes are very harmful. That is because as the different type of data is mixed inside the SSD, they causes the high write amplification in SSD. So when the small random writes are occurred in the application layer, then the high write amplification will be harmful to the SSD. However, if the application gives some large sequential writes to the SSD, then as the same type of the data are located in the same single length block, they are very good in case of SSD. So LSTM-based key value store like RocksDB or LevelDB is well known to be very SSD-friendly application because they say that we guarantee the sequential write. So let's just look about the basic of the RocksDB. RocksDB is popular LSTM-based key value store engine which write and delete data in unit of the file, and the default size is the 64 megabyte. So if in ideal case, as you can see in the figure 4, which is on the right side, the whole file located in a single length block so that they are deleted at once. And if they are deleted at once, then all of the data is invalidated in a block so that we can reach to the optimal WAF of 1. So we have modeled these optimal cases using the FIO tool. In FIO tool, when we issued the 64 megabyte of the block size write with buffered IO, then we get the average length of the issued sequential writes, same with the sequentially allocated LBA size, and we can get the WAF of optimal WAF 1. So we can expect that when RocksDB really guarantees the sequential writes, then the SSD internal WAF can reach to the 1, which is the optimal WAF. However, according to our experiment, as the RocksDB cannot guarantee the sequential writes in real, so that you can see, as you can see in the CDF graph on the left side, only less than 20% of the data is issued in the 64 megabyte, and they are splitted and interleaved on somewhere in the file system, so that the WAF reaches over the 4.5. So this is very different than what we expected before. So we are saying that RocksDB say that we guarantee the sequential write, and this is really friendly to SSD. However, according to our observation, in some reason, they cause some split and interleaving inside the file system. So inside SSD, the higher WAF is caused in somewhere. So as it is just a working in progress job, so we are just searching for the solution and realize the main reason. But the main reason is because there are a lot of multi-threaded writes, sequential writes, so that the concurrent writes are interleaved in lower layer, so they are split in lower layer. This is not only a problem of ext4 file system, but there is a lot of file systems which has the same problem with the ext4 file system. And some may think that it can be solved using the open channel SSD or multi-streamed SSD or something like that. However, We think that our opinion is that if RocksDB or LSTM-based key value store is really SSD friendly, then it must be friendly to the general SSD. So we are saying that there is some problem and it is not that friendly in real. So we are just working in progress to solve this problem and working for the main contribution why small random writes are causes. Yes, thank you.
Thanks, Lee. Questions? Well, is there, oh, yes, there's, I didn't realize, all sorts of surprises.
Yeah, I'm Ted Cho, Google. I'm wondering if you look to see if there are many other applications that might be doing simultaneous sequential writes and whether or not the conclusion ought to be that flash translation layers should just simply be better at this workload if it's in fact very common.
Yeah, I think that is right because I want to see the other, what will be acted if we run the other applications, but we conclude this as there is a problem is the concurrent write is because according to our observation, the concurrent writes, if we change the number of the concurrent writes, then the result is different. So, but it is also good to see the other application and the working in the lower layer. Yeah.
Okay. I mean, I do wonder if, in fact, it's deep in the write-back logic, but, you know, I mean, it does seem that you might be able to work around this with, you know, fallocate and direct I/O and so on. Whether that's actually what you want to do or not is a different question.
Yes, we have also another experiment result using the direct I/O, and we get also a high write amplification and write split occurs using the direct I/O with high 64 megabytes writes. So we think that direct I/O is not the right away ideal solution right now. Yeah. Thank you.
So, good afternoon, everyone. I am Hee-jin Yoon, and actually the author of this work cannot attend this conference, so I will help you to present uncovering critical data in launching mobile applications to improve user experience at low cost. So, and they didn't give some presentation files, so I have to present this with a poster. So let's start. Application launch time is an important user experience metric for mobile device, but the latency of page cache misses occupies a large percentage of application launch time. So the previous works reduced the page cache misses during application launching by prefetching soon-to-be-used applications to the page cache. However, this proposal have to prefetch multiple massive files to the main memory, which can stretch applications' own data and degrade the performance of applications. So in this paper, we first investigate the root cause of these page cache misses and systematically study data access behavior of multiple applications in Android. So based on our analysis, we observed that an extremely small set of the data, which is 0.3% on average of total data used to launch an application, is responsible for most of the page cache misses. So we define this set of data as a critical data. And by utilizing critical data, we can improve applications launching process. Specifically, there are 4 methods can be used. Firstly, we can lock the small size of critical data in the page cache to reduce the launch latency with a trivial overhead because the route critical data can significantly reduce page cache misses. Secondly, the critical data can be accompanied with an application prediction algorithm to speed up the launch time for the predicted soon-to-be-used applications. Instead of multiple massive files, only the critical data of each predicted applications should be pre-patched into main memory. Thirdly, critical data can be used to optimize a read-ahead mechanism of memory to pre-patch critical data for fast application launching. Lastly, the page cache eviction algorithm can be improved to avoid evicting critical data. To identify and utilize the critical data, Find CD and Lock CD framework is proposed. Find critical data set, which is Find CD, is designed to systematically find critical data for a given application with a low overhead. And Lock critical data, which is Lock CD, is used to make sure that critical data in memory until it will be not used. So this work evaluates Lock CD and Find CD with 20 commonly used mobile phone applications. The results show that it can reduce application runtime 11% on average with negligible overhead, and its benefits independent of mobile device and kernel versions. So thank you for listening, and if you have any question, please contact via email behind of this poster. Thank you for listening.
Thank you so much. Questions? All right. While she's setting up, our final speaker is Samantha Miller from UW.
Hello, I am Samantha Miller from the University of Washington, and I'm going to talk about performance-safe extensibility for Linux kernel file systems. So this is fast. People here write file systems, and you sometimes want to implement those file systems in existing operating systems. So what would you really want out of a file system extensibility framework that will allow you to implement your file system in some existing operating system? Some of these properties are high performance. You would want your framework to have very low overhead so that your file system can be used for performance-critical applications. You want safety. There should be resilience to bugs in the file system, ideally both within the file system itself, and particularly you want to limit the impact of those bugs on the wider operating system. You want some general programmability. You don't want to limit what you can do with your file system too much. You want to be able to implement lots of different things with your file system. And online reconfiguration. You want to have developers to be able to redeploy file systems without service downtime to enable the fast development cycles that many companies need today. However, the existing techniques for file system extensibility in Linux don't sufficiently provide all of these properties. The virtual file system layer that exists in Linux today is really great for performance and flexibility of file systems, but it's complicated and difficult to implement correctly. This means that bugs written or file systems written using the VFS layer are more likely to have bugs. Additionally, this does not support online reconfiguration. Fuse allows implementing file systems in user space, which gives resilience and general programmability with the Fuse interface. However, Fuse has high performance overhead, up to 83% for metadata-heavy workloads. There's also eBPF, the extended Berkeley packet filter, which is originally designed for networking, but has recently been extended to allow portions of a file system implemented in the kernel. However, eBPF is designed for small pieces of code and is not sufficient for implementing large modules, at least easily. We want to provide a framework that provides all of these properties. Our approach is to combine the safe interfaces with a safe language in order to enable performance safe file systems in Linux. Our framework is a thin layer that runs between the kernel, mostly the VFS layer, and the file system that exposes the Fuse low-level interface to file systems running inside of Linux. File systems written using our framework are implemented in Rust, almost entirely safe Rust. Rust is a type-safe, memory-safe, data race-free programming language with performance similar to C, allowing it to provide safety without overhead. Our past work has shown that Rust is able to eliminate a very large percentage of low-level bugs that don't depend on file system semantics that could cause kernel panics. As future work, we also want to implement more features for faster development, like online reconfiguration. This is the design of our framework. The shim layer is our framework that runs between the VFS layer and the file system. The top portion here is a modified version of the Fuse kernel module that translates between the VFS interface and the Fuse low-level API that's provided to file systems. The lower portion provides wrappers around a set of kernel functions that are necessary to implement file systems, right now primarily block I/O. So far, we've implemented the XV6 file system using our framework and have been running file benchmarks running on a RAM disk. We found that the file system implemented using our framework is able to have performance almost identical to a C implementation in the kernel, and both are better than Fuse performance on metadata-heavy workloads, in this case, varmail from FileBench. In conclusion, we believe a file system extensibility framework should provide high performance, bug resilience, general programmability, and online reconfiguration, among other development features. We are trying to build a framework that provides all of these features to file systems in Linux. As future work, we want to implement more features in our framework, including rapid redeployment and anything else that any of you have strong feelings toward, please tell me. And our preliminary evaluation shows that this is able to have performance very, very close to the C implementation in the kernel. Thank you.
Awesome, thanks. Questions?
Is it working? Yeah, okay, cool. Thank you for an energetic talk, and it's pretty cool seeing Rust running in the kernel. So you mentioned the general programmability. So there are quite a lot of libraries already in the kernel, and so let's say I'm writing a file system inside of which I would like to use the cryptographic library, which is already in the kernel. Do you envision being able to call from this MyRust file system the functionalities that are already available in the kernel safely?
Yeah, so that's the bottom portion of our framework that has to provide wrappers around a set of kernel functions. So far, it's primarily block I/O because that's what we've needed so far, but there's no reason that it couldn't be lots of functions within the kernel, and it's certainly going to be future work as we continue to work on this project to implement more and more functions that are wrapped safely.
And so that wrapping provides safety, more safety than calling it directly if I would not use Rust, is that the case?
Yeah, so you would be able to use Rust, we provide safe Rust wrappers around those functions, so you would get the guarantees of Rust.
Right, thank you.
Mm-hmm.
No microphone here, so I'm just talking my normal volume. How hard would it be to port something like this into the Darwin kernel?
I don't actually know the Darwin kernel. Can you explain? Oh, BSD? Mac OS? So I don't really know the specifics of what the file system layer looks like in that kernel. So that would really be my question. Presumably, you can use Fuse on Mac OS, right? So it shouldn't be difficult because since we're reusing the Fuse kernel driver, you should be able to do the same in the Darwin kernel.
Thank you.
Thanks.
With that, let's thank all of our speakers.